In the previous video, we discussed the concept of loss of load probability, which is a decisive parameter in a standalone PV system. In this video, we are going to learn how to model the battery. That is a crucial step when carrying out the detailed design of the standalone PV system. The first learning objective of this video aims to recap the working principle of a battery by looking at its equivalent circuit and IV curve. The second is focused on determining the operating voltage of the battery bank. As you know, a battery is connected at the DC side of the standalone PV system. Basically, current from the PV modules will either flow towards the battery or towards the loads. If the loads demand more current than the PV modules can produce, current will flow from the batteries to the loads. Thus, they provide a source of stable power inside the PV system, thereby becoming a crucial system component. For this reason, it is important to understand how the battery will act during the operation of the PV system. To understand this, we have to first consider the net effect of all the components that charge or discharge the battery. The figure shown here is a detailed topology of the standalone PV system. It consists of the PV modules, characterized by its maximum power point, current and voltage. This is due to a MPPT employed in the PV system. Then you have the charge controller, which has 3 ports that connect it to the PV modules, inverter and the battery bank. Each port is characterized by its own current and voltage. Finally, after the inverter, you have the load with its own current and voltage. Before we proceed further, you have to remember that the maximum power point tracker does not form a separate device in your PV system. Usually, the MPPT is embedded as a power electronic component inside the charge controller. Sometimes, the MPPT, charge controller and inverter are even embedded into a single device. These different parts are linked together inside the device through sub-circuits, each performing its own function. Whatever is the type of device used, the energy flow inside them will be like the topology depicted here. Let us now briefly recap the equivalent electrical circuit and the IV curve of a typical battery. In the video Introduction to Battery, you studied that a battery is represented by a voltage source connected along with a series resistor. The voltage source denotes the open circuit voltage of the battery, while the series resistor represents the internal resistance, Ri, faced by the charge carriers during the charging and discharging process. From this, the voltage of the battery, VBB, is represented as VOC-BB plus product of IBB and Ri. Here, IBB is the current flowing into or leaving the battery, which is positive when the battery is being charged and negative when it is being discharged. Suppose when the battery is charging, it means that the current is flowing into the battery and is denoted by this IV curve. From this IV curve, you may notice that for a certain current level, the operating voltage of the battery is greater than its circuit voltage, open circuit voltage. On the other hand, if the battery is discharging, which is represented by this IV curve, the current flows in the opposite direction. Hence, for a certain current level, now the operating voltage of the battery becomes smaller than its open circuit voltage. From this, we know that depending on the charging or discharging process, the voltage of the battery will be slightly greater or smaller than its open circuit voltage. Further, the open circuit voltage of the battery bank is itself a function of state of charge, temperature, and other parameters. Thus, in reality, the open circuit voltage will also vary depending on the operating condition of the battery. But this parameter is simplified in this design step and is assumed to be constant value under all state of charge and temperature changes. It is assumed to be equal to the rated open circuit voltage VOC0BB of the battery bank. Now, going back to the topology of the PV system, let us look at how the power is transferred from one component to the other. First, we start by looking at the left-hand side of the system topology. Here, the power generated by the PV modules, derated by the efficiency of the maximum power point tracker, is equal to the power received at the input port of the charge controller. This is expressed by the following equation. From this equation, an expression for current entering the charge controller ICC is obtained. Further, in order to simplify the calculations in the later stages, the numerator of the ICC equation is represented by a variable beta. Next, let us look at the right-hand side of the system topology. Here, the power required by the loads, PL, is equal to the product of AC current and AC voltage leaving the inverter. This is, in turn, equal to the power at the input side of the inverter derated by the inverter efficiency. Thus, from the following expression, the current at the input side of the inverter, IM, is obtained. Similarly to the previous step, to simplify, the variable alpha is used instead of the ratio between the power required by the loads and the inverter efficiency. Finally, from the expressions for the charge controller and inverter currents, the current flowing through the battery bank IBB is obtained. It is expressed as ICC minus IM. Substituting their corresponding variables in this equation, IBB is obtained as beta minus alpha divided by VBB, where VBB is the voltage of the battery bank. As already mentioned, VBB can be written as a function of the battery bank open circuit voltage, series resistance, and its current. Thus, by substituting the obtained expression for IBB in this equation, a quadratic equation in VBB is obtained. This quadratic equation should be solved for the variable VBB. Two solutions can be obtained after solving that. Out of these two solutions, the correct one is the one using the positive sign. This is verified by assuming a situation where there is no power flow in the PV system, that is when the circuit is open. This means beta minus alpha term in the solution will be equal to 0, and the voltage of the battery will be equal to its open circuit voltage. To conclude, this video focused on the modeling step of battery bank to be deployed in the detailed design strategy of standalone PV system. The expression to model the voltage of the battery bank is derived in this design step. In the next design step, the already familiar energy balance approach will be implemented to size the different components in the PV system.